Picture this. You've got exactly 20 minutes left on your Physics 0625 mock exam. The timer is ticking down, the invigilator is pacing the aisles, and you flip the page, only to be met with a massive, twisted, curved graph. Honestly, this is the exact moment where your grade boundary is decided. So let's jump straight into this high-stakes rescue and get you ready.
Because staring blankly at a complex, curved speed-time graph while under immense pressure, yeah, that is exactly where most students just bleed easy marks. The curve changes, the gradient shifts out of nowhere, and total panic sets in. But here's the secret. Those hidden marks are actually entirely predictable if you know exactly what the Cambridge examiner is hunting for.
And this right here is the painful mistake that costs students their top grades. Just listen to this answer. She falls fast, then stops. Ouch. That is a classic vague learner mistake that instantly triggers a harsh 0-mark penalty from the examiner. I mean, it lacks scientific reasoning, completely ignores the actual data on the axes, and totally misses the physical context of what's actually happening.
Section: Motion Graphs Master Key. Let's get right into it. To dodge these traps entirely, we need a systematic framework to decode literally any Cambridge physics graph without a single second of hesitation. So let's break down this crucial data showing exactly what the differences are, because the differences here are absolutely everything. On a distance time graph, the gradient equals speed, and a horizontal line just means the object is stationary. Simple, right? But look really closely at the speed time graph. Here, the gradient equals acceleration. A horizontal line means constant speed, and the area under the graph is your distance traveled. Mixing these up in the exam room is an absolute disaster.
And honestly, this brilliantly illustrates why ordinary revision just falls flat. You know, you can memorize physics formulas all day long, but examiner reports highlight these specific recurring errors year after year. We're talking missing units in your final answer, writing vague explanations like she falls fast, confusing your x and y axes, and rounding your calculations way too early. Knowing these traps exist, that's half the battle won right there.
Section: The Parachutist Plunge. Okay, now that we have our master key, let's apply it to a classic, high-mark Cambridge-style example. Notice immediately the changing shape of the curve here. Speed is our dependent variable, over on the y-axis, and time is our independent variable on the x-axis. Your golden rule for this? Whenever a graph line changes shape, a brand new physics description or calculation is required. Let's chop the physical context of this complex curve into highly testable step-by-step bites. So at point A, the parachutist starts her fall. Her speed increases, which means she is accelerating. Notice that really steep gradient? Well, by point C, the curve flattens out. The speed reaches its absolute maximum value and stays exactly the same. Then, bam, at point D, the parachute opens, the speed decreases rapidly, and we get this very steep, sudden drop. That's high deceleration. See what we're doing? We're translating a visual curve straight into precise physics terminology. So the crucial takeaway is what's happening precisely at that flat line between C and D, and then again at point F. This is the exact examiner-approved definition you've got to use on your paper. Terminal velocity is a constant speed reached when acceleration is exactly 0. Whatever you do, do not write she stops. Her acceleration stops. She's actually still moving downwards, just at a steady, constant speed. Okay, time for a quick active challenge. I want you to pause and predict. Looking at the entire curve, where exactly on this graph is a negative relationship shown? Scan those letters, lock in your answer in your head before the virtual timer runs out. Got it? Are you looking at the gradient? Let's see if you nailed it. A negative relationship is simply where there's a downward sloping line. This happens from point D to E to F, and then again from G onwards as she finally hits the ground. It just means that as the time values on the x-axis increase, the speed values on the y-axis fall. It's literally just a visual representation of deceleration. Section: Spot the flawed answer. Let's look a little closer at this. All right, let's escalate the stakes a bit. I want you to act as the tough Cambridge examiner for a second. Look at this side-by-side comparison. On the left, we've got our vague, flawed student answer, she falls fast, then stops. That gets absolutely 0 marks. No way. Now look on the right at the mathematically precise, mark-winning phrasing required for top bands. Terminal velocity reached, acceleration is 0. Do you see the stark difference there? The right side uses the correct conceptual vocabulary and precise motion descriptions. It's night and day. And this brings us to your ultimate weapon for the exam: I am handing you the perfect 4-step formula needed to construct a bulletproof, top-tier exam response every single time you see a written question. First, state the concept. Second, back it up with evidence or specific data extracted straight from the graph. Third, apply your scientific reasoning to link the data back to the concept. And finally, wrap the whole thing up in that precise examiner wording we just practiced. So let's put that formula to the test and extract some specific data. Look really closely at the lower flat line on the graph, right around point F. The question is, for how long was the parachutist traveling at exactly 5 meters per second? Try finding 5 on the y-axis, tracing it horizontally over to the line, and looking straight down at the time axis.
Did you spot the start and end times? The flat line at 5 meters per second starts at exactly 35 seconds and ends at 60 seconds. So you just write down 60 seconds minus 35 seconds, which equals exactly 25 seconds. Pro tip here, always show that simple subtraction working on your paper to secure those final calculation marks. Never just guess it by looking.
You guys have done brilliantly so far. You've completely decoded the graph, you've locked down the exact terminal velocity definition, and you've secured your calculation marks. But listen closely, because this is huge. In a moment, I'll show you the hidden examiner clue that changes the practical answer completely. But first, you need the framework that makes that clue obvious, because knowing how to read the graph just isn't enough if the practical setup used to get this ticker tape data is fundamentally flawed from the very start. You've mastered the theoretical graph and all the terminology. But what if the practical apparatus used to capture this data in the exam paper is totally flawed? Well, we're going to cover exactly how to spot those traps in our next explainer. Until then, ask yourself this. If your ticker tape timer is running slower than it should, how would that secretly warp every single calculation you just made? To find out, subscribe to our YouTube channel, Ace the Exams, at acexams_IGCSE to excel in your Cambridge examinations, and click on the next explainer right now to master the mock survival plan.